Hello students, in this video we're going to solve this problem where we have a function defined as an integral. This happens quite a bit, especially in special functions, probability and statistics, when you have probability density functions, shows up in differential equations. So this is a lot more common than I think students may think when they first encounter this type of problem. But anyhow, let's go through solving this problem. And if you just, it almost seems like nothing happens when you actually compute the derivative. Some people think like, well, it looks like you just put the x inside of the integrand here, and the answer is going to be square root of x cubed plus 8. And that is the answer, actually, at the end of all this. But let me just quickly go through the justification for that so you can actually see what's going on underneath. So let me just quickly take you through that. So the fundamental theorem of differential calculus, or the fundamental theorem of calculus, the derivative form, this would have been the form actually first thought of by Newton. If you'd asked Isaac Newton back in the day what he thought of as the fundamental theorem of calculus, he would have thought of it in this version. So you take the derivative of this integral, and it looks like you just put the x in for t and you get f of x, okay? Well, there's actually a lot more going on there, and I'm not going to go through a proof, but I'm just going to give you a justification for what's going on here. Like, what happened to the a, for example, is oftentimes a question I get from students. So suppose that capital F is an antiderivative of the integrand, little f of x. All right, now another way of saying that is that if you take the derivative of the antiderivative, you get the function back again. That's not so mysterious, okay? Now, as it may first look, okay? The prime means we're taking derivative with respect to the independent variable, which is x. Now, that's important because if you look back here, t is a dummy variable. X is the input variable, and x is the variable with which you are differentiating. We're not differentiating with respect to t. We're differentiating with respect to x. The input is the upper limit of integration. When you input something into this function, you're inputting for x, not t. So if you were to input a 2, for example, then you would be putting a 2 up here for this upper limit of integration, and then you would integrate, and you would integrate from whatever a to 2 is. Okay. So when you take a derivative of the antiderivative, that's f prime of x, the prime being the differentiation with respect to x, you get the integrand. Let me give you an example. X cubed is an antiderivative of 3x squared. Now, when I use the term antiderivative, this is not an indefinite integral, so I do not have the plus c. Some people call the antiderivative, they include the plus c in their definition of antiderivative. I follow more along the lines of the differential equation school of thought. So for me, an antiderivative is the without the arbitrary constant, and then the indefinite integral has a plus c in it. So what does it mean to say that x cubed is an antiderivative of 3x squared? It means that, let's go back to my wording here, capital F of x is an antiderivative, x cubed is an antiderivative of 3x squared. So that means if I take the derivative of the antiderivative, if I take derivative of x cubed, of course I'm going to get 3x squared, which is of course little f of x. So you just get the integrand back again. Okay, now let's move through this a little more quickly. That's what that phrase means. The derivative of the antiderivative is the integrand. So suppose in general that you have a function defined where the input variable, the independent variable, is the upper limit of integration. Now you know from your fundamental theorem of calculus, integral calculus, the integral form, you take the antiderivative and then you plug in the upper limits of integration, you plug in the lower limit of integration, and you subtract the two. Now watch what happens when you differentiate the left-hand side and differentiate the right-hand side. If I differentiate the left-hand side, that just stays as it is. That's our symbol there. I take the derivative of capital F with respect to x. X is the independent variable. Again, that's important. It's not t. T's a dummy variable. I take the derivative of f of a with respect to x. Now, look, f of a is a constant, f of a is a constant. For example, if I plugged in 2 here, I would have 8 for capital F of 2. So I have f of a is a constant. The derivative of the constant, of course, is 0. I have d dx of capital F. Okay, so that's going to become f primed of x, which is, of course, going to give me little f of x. So you see how that's going to play out. I'm just reminding you, x is the independent variable. That's the input variable. There's another way you could think of it. T is just a dummy variable. We could have put any letter in here. S, we could have put, Z. Most often you'll see T. All right, so now let's follow through. So that means that if I take, I just bring this down, if I take the derivative of this integral, of this function, which is defined as an integral where the input variable is x and that's the upper limit of integration, then I took the derivative of capital F, I get f primed, where the prime means derivative with respect to x. The derivative of the constant is 0. And of course, capital F primed of x is equal to little f of x. That harkens back to what I have written up here. All right, that's it. That's all there is to this problem. So solving this looks rather simple, but all of this stuff on the right-hand side is what's going on underneath. So if you want to pause the video and just write your answer down, by all means, please give that a try. And then come back and hit the play button and you'll see, here's our answer. Little f primed is equal to the derivative of this integral where the upper limit of integration is the independent variable. So I'm taking the derivative of a function where the input function is an upper limit of integration with respect to x. Of course, I'm invoking the fundamental theorem of differential calculus. That's all this business here on the right-hand side. And when I do that, I somehow pretend I know what capital F is, even though I may not know, but then capital F prime just gives me the integrand. The 0 corresponds to the fact that I had a 2 inside of here. And so the derivative of constant is 0. Now you could probably could you skip this step? Yes, and you can just write this as your answer. But I just wanted, what happened to the 2? You differentiated and you differentiated that input and there was a constant and so you got a 0. So the 2 got input and then you differentiated it and it was annihilated. And then little f prime of x is of course the integrand. All right, good luck.